Assalamu alaikum. Hope you are doing fine. The resistivity of a substance depends on temperature. It is known as temperature coefficient of resistance. In this video, we are going to learn about temperature dependence of resistance. To demonstrate temperature dependence of resistance, I take a graphite lead which is used in pencil. I connect the ends of this pencil lead to the crocodile clips. Then I connect these crocodile clips to the probes of multimeter. Now I will set the multimeter to read the resistance. Now you can observe the multimeter gives the resistance of this graphite lead. Now I will heat this graphite lead to check what happens to its resistance. Now before heating this, the value is around 8.9 ohm. I'll heat this with the help of this lighter. See what happens. As you can observe, as I am heating this, the resistance is constantly decreasing. Resistance is decreasing. This shows that carbon is said to have negative temperature coefficient of resistance. It means when the resistance of a substance or the resistivity of a substance decreases with temperature, means the object is said to have negative temperature coefficient of resistance, that is minus alpha value. The resistivity of a substance depends on temperature. Experimentally, it is found that the resistivity of conductor increases with increase in temperature. According to the expression rho T equals to rho naught into 1 plus alpha into T minus T naught. I take this as equation number 1. Here rho T stands for resistivity at temperature T and rho naught stands for temperature resistivity at temperature T naught. Here T naught is nothing but a reference temperature. Usually it is taken as 20 degrees Celsius, and alpha is nothing but temperature coefficient of resistivity. Now from this equation number 1, I will get the expression for alpha. For that, I will multiply rho naught with each term. You see how I do it? Rho T, rho naught is multiplied with 1, so we get rho naught. Then it is multiplied with this term, alpha rho naught, T minus T naught, something like this. Then rho naught is taken to the left hand side, so it will subtract rho T minus rho naught. Then here this term remains. Afterwards, I take this term to the left hand side. By doing so, only alpha remains on the right hand side. So alpha, the remaining terms are brought to another side and we get the expression something like this. Now I rearrange it. So it gives me the expression for alpha, which is nothing but temperature coefficient of resistivity. Rho naught T minus T naught. Now this expression can be written as alpha equals to delta rho upon rho naught delta capital T. Here delta rho is change in resistivity for a change in temperature delta T. Now I box this. I take this as equation number 2. Here temperature coefficient of resistivity have a unit of alpha is per degree Celsius. This is the unit of alpha. Now we will discuss the temperature coefficient of resistivity of conductor. We know conductor is a substance which allows the flow of current. Take alpha for conductors. You always remember, in case of conductors, when temperature increases, resistivity also increases. This shows that conductors have positive temperature coefficient of resistivity. It is alpha is nothing but plus or positive. Now, what is the reason for this increase in resistivity when we increase the temperature? In any substance, electrons are present. When we heat the conductor, the electrons present in the conductor starts moving fast. Their velocity increases, which results in the increase of kinetic energy. So they collide with each other. As a result, the the resistivity increases. So this variation in resistivity with temperature can be shown with the help of a graph. I draw a graph between temperature taken along its axis in Kelvin and resistivity. The unit of resistivity is ohm meter. It's taken along y-axis. The graph obtained here is a linear graph. This shows that when temperature increases, resistivity also increases. But here, this graph, which is linear in nature, shows non-linearity at a low temperature. At this point, at very low temperature, it shows non-linearity. It is not straight. You can say it's slightly bent here. It's slightly curved here. This non-linearity is shown at low temperature. And it is observed that when temperature is 0 Kelvin, when temperature is 0 Kelvin, we call it as absolute 0. At absolute 0, the resistivity becomes rho naught. It becomes finite, very small. That's all about alpha for conductors. Now we'll discuss temperature coefficient of resistance or temperature coefficient of resistivity for semiconductors. Before going ahead, we get an expression which looks alike to equation number 1. We know resistivity depends on resistance. Now, we have already learned that resistance is directly proportional to length of the conductor and inversely proportional to area of a cross section of the conductor through which current is flowing. When we combine these two expressions, we get this. R is directly proportional to L upon A. Now, when I remove this proportionality, here we include equal to sign along with a constant. That constant is like what? Rho. That is resistivity. L upon A. Now, this resistivity rho can be represented as RA upon L. Now, what is the area? Area is something what? Length into breadth for a rectangular object. I consider the conductor to be in rectangular in shape. So, it becomes L into B upon L. Here, L and L will cancel. What do we get? We get the expression for rho as R into B. Suppose here B is taken as L. Then you get the expression for rho as R into L. Now, here it means that length of the conductor is equal to its breadth. So, rho is obtained to be equal to the product of resistance and length. That means the unit of rho is ohm meter. Here resistance is measured in ohm and length is measured in meter. This is how we get the unit for ohm. Unit of resistivity. Now this shows that resistivity depends on resistance. So equation 1 can be written as RT equals to R naught into 1 plus alpha into T minus T naught. I take this one as equation number 3. Here RT stands for resistance at temperature T and R naught is a resistance at temperature T naught, which is nothing but a reference temperature, as I told you earlier, and it is usually taken as 20 degrees Celsius. So in this way, the expression for alpha can be obtained by following the same method. RT, I multiply R naught with each term. Now, R naught, when multiplied with 1, then I multiply R naught with this term. So I get alpha into R naught into T minus a T naught. My aim is to get the expression for alpha. So I keep alpha here. Remaining terms are taken this side. Before that, I will take this term to the left hand side. I'll get RT minus R naught equals to alpha R naught T minus T naught. Now, alpha is kept here. I bring this term to the left hand side. It is multiplying here. When it is taken to the next to left hand side, it will divide. RT minus R naught upon R naught T minus T naught. Now, this can be written as alpha equals to, in the place of RT minus R naught, I use delta R upon R naught. In the place of T minus T naught, I write delta T. Here, delta R is change in resistance for a change in temperature. That is nothing but delta T. This is another expression for alpha, which stands for temperature coefficient of resistivity. I take this as equation number 4. Now we will discuss the temperature coefficient of resistivity for semiconductors. When temperature increases in semiconductor, it results in the reduction of resistivity. This provides a negative value for alpha. So alpha is negative for semiconductors. Now if I draw a graph by taking temperature along the x-axis and resistivity along a y-axis, then we get a curve, something like this. This shows that resistivity decreases with increase in temperature, whereas in case of the conductor we get a linear graph. Now the temperature dependence of substance can be understood with the help of this equation. Now we know this. Sigma equals to N E square tau upon M. This is the equation we have obtained earlier, and this represents conductivity. Here sigma stands for conductivity. We know resistivity is the reciprocal of conductivity. Here rho equals to 1 upon sigma. So from this equation, rho is equal to m upon n e square tau. Now if you look at this equation carefully, you may find that it has got m. M is mass, which is a constant, and E is the charge of electron, which is also a constant, whereas n, the number of electrons, and tau, mean free time. These two do not remain same, so they are variable. Now this equation can be written in this way. Rho is equal to m upon E square into 1 upon n tau. Here m upon E square is a constant. It is a constant. So I can write this equation as rho equals to constant multiplied with 1 upon n tau. When I combine constant with equal to sign, we get a proportionality. So rho is inversely proportional to n tau. This shows that rho is inversely proportional to n and also inversely proportional to tau. So rho will decrease when n increases and also rho decreases when tau increases. This is what it means. I hope this video is useful. If you have any kind of doubt related to the topic, can you put your questions in the comment section? Thanks for watching.